Okay, so Stefan is a software engineer at Google. He works on the SDN controller for Google's network, where he leverages the P4 language to improve how switches are controlled and validated. Prior to coming to Google, he got his PhD at Stanford, where he worked on program analysis and software synthesis. So pleased to have you, Stefan. Take it away.
So Nate's thanks to the organizing committee and people who made this event possible. So good morning, everyone. I hope you're all doing well. Today, I'd like to talk about how we do optimal L3 routing at Google and how we use P4 and P4 Runtime specifically to achieve that. So as many of you know, the pervasive topology in data centers is called a Clos topology. And so Clos topology is this hierarchical assembly of a lot of small switches, sort of these commodity switches that are relatively easy to buy, to build what you can think of as a large virtual switch with many, many thousands of ports that allow you to connect the large number of servers that you have in a data center. And so here on the left, I'm showing a 5-stage Clos topology, where stage 1 at the bottom is the top of rack switch, where underneath that top of rack switch, you would have the actual machines. And then in different communities in different places, the terminology is a little bit different, but sometimes stages 2 and 3 collectively are called the middle blocks, and stages 4 and 5 are often called spines. And so one really nice property in these topologies is, of course, there's many, many redundant paths between any two nodes. And that makes them highly fault resilient. So for example, if we want to have two nodes talk to each other, marked in red here, so one node will be underneath this door over here on the left, one on the right. I've just marked two of the paths that a packet could possibly take. And in fact, there's actually many more. And the way you do routing in these topologies is actually very simple. So the way you utilize this like largely redundant set of paths that you could be taking is you can do what is called equal cost multipath, or ECMP for short. So essentially at any stage, you take all of the possible paths and you just equally divide your packets among all of these links. So in particular, if you start at this TOR at the very left, you just ECMP over all of the links that it has to the stage 2 switches. So for the red path, it might take this first one. And then the stage 2 switch does the same thing again, where it ECMPs over all of the uplinks towards the S3 switches. And then you do the same thing on the way down. And so this is really beautiful. These Clos topologies, sort of from a theoretical standpoint, are highly symmetric, and routing with ECMP basically gives you sort of optimal results. Unfortunately, in reality, these Clos topologies are often quite imbalanced, and there's a lot of asymmetry that you have in real deployments. And so ECMP routing is not actually going to be optimal. And so I want to first go over some of the reasons that you might have this imbalance. So the first reason, and I'm now sort of zooming into these Clos topologies a little bit to make the examples a little bit smaller. So what I'm showing here is a 2-stage Clos topology with 3 switches on each stage. And so the first sort of restriction you have is, unless your number of uplinks at any given stage is the same, or at least an integer multiple of the number of switches in the next stage, you can't evenly divide those uplinks. So in this particular example, I'm showing these switches. They have 4 uplinks each, but there's only 3 switches in the next stage. And so naturally, the only thing you can do is basically have 2 uplinks to one of the stage 2 switches, but then only a single uplink to the remaining ones. Now, of course, if you do sort of the naive ECMP routing, and let's say there's going to be a host on this first S1 switch that wants to talk to the switch over here on this last S1 switch. If you just do ECMP routing, then the picture looks as follows. So let's assume this host wants to send 12 gigabits per second of traffic towards that other host. And so you do ECMP routing, which means there's 3 gigs flowing on all of these links. And And very naturally, because there's two uplinks to this one S2, this S2 now has to send 6 gigabits of traffic towards the last S1 versus there's only going to be 4 coming from these other ones. And so clearly there's some imbalance and your links are not going to be utilized very effectively. On the other hand, if you could do a unequal cost multipath, so you send different amount of traffic on different links, you can actually balance the situation out quite easily. Right? If you have 2 uplinks, you can send 2 gigs of traffic each on those uplinks and send a little bit more on these individual links so that the traffic coming from the S2s towards this S1 on the right here is all going to be balanced. Unfortunately, there's even more cases of where imbalance can come from. So even if you manage the number of uplinks to be an integer multiple of the number of switches in the next stage, of course, these data centers are huge. And so at any given time, there's always going to be some number of links and some number of nodes that have either failed or maybe they have to be taken out to be upgraded or are just otherwise unavailable. And so again, to illustrate that with an example, I'm showing here a very simple 2-stage Clos topology with 4 switches. And right now, all of these links are basically sending 3 gigabits per second of traffic towards S2 switches, and then each S2 switch has 2 uplinks where it just sends that traffic on. And let's assume in this example that the links are have 4 gigabits per second of capacity. So now, if we imagine that one of the uplinks of this first S2 switch goes down, so that switch or that link fails, or maybe the thing that is connected to fails, that node failed. In this case, this S2 switch can take some of the traffic that used to flow over this link and move it over on the other link. So now this link can carry 4 gigabits of traffic. But because it's a 4 gig link, you actually have too much traffic going to this S2, right? There are 6 gigabits reaching this S2, and so 2 of those need to be dropped. And that's really unfortunate because if you could do a little bit smarter unequal distribution of traffic early on, like I show in this example, you can actually send all of the traffic without hitting any limits in your capacity. So the S1 switches, if they can send traffic towards the two S2 switches in an unequal way, basically noticing that this S2 has reduced capacity because one of its uplinks is broken, they can essentially make sure that they send less traffic towards that S2, so 2 gigabits in this example, and send more traffic towards the other one. And in this case, no traffic has to be dropped. Okay, there's one more example that I want to highlight that can cause imbalance. So in this picture, I'm showing one of our Google data centers. I think this is the one in Iowa. And as you can see, these are like basically huge rooms filled from left to right and front to back with servers. But this is not actually how these data centers start out when they're first built. So when they're first built, the building is already the same size, but we actually start filling them with just a small number of servers. And then we incrementally deploy capacity as we need it. And there's many reasons that you don't want to start out with a data center that's filled to the brim with servers right away. One is obviously cost. That's going to cost a lot of money to build that from the get-go. But maybe more importantly, if there's going to be capacity that's just sitting there and isn't yet used because you don't actually need the full data center just yet, those are going to consume electricity and just generally cost to upkeep them without doing any real work. And even worse, by the time maybe a year or two down the line, when you actually do need that capacity, that hardware might already be outdated. And so if you had waited with buying it, you could actually buy newer hardware for a similar price and basically sort of leapfrog the generation of switches, the generation of hardware that you deploy. And so it's very common that you want to have these incremental deployments. And what that means is that these Clos topologies sometimes become imbalanced or not optimal because you don't want to go to the full sized just yet, and you want to be able to incrementally deploy more capacity as needed. Okay, and so with all of these examples, I've basically highlighted that equal cost multipath, even though optimal in sort of the theoretical a fully symmetric example, in practice is not going to really cut it. And so really what you want is called weighted cost multipath, or WCMP for short. And we found that Google in our data centers, this is really crucial to making optimal utilization of our network. And the way we actually implement this is that we use software-defined networking, which means we have a centralized controller that essentially implements all of the control protocols, and it has a channel to each of the switches through which it can communicate what kind of forwarding entries you want to install on these switches. And in particular, it can essentially allocate the weights and then distribute them to all of the switches. So specifically, the way these weights are allocated in our centralized controller is a relatively complicated computation, but it can make use of a lot of available information. So obviously, first and foremost, it's going to look at the available capacity of the different links to make sure that links are being utilized in an optimal manner. It also knows the entire topology. Since it's a centralized controller, it's sort of a bird's eye view of everything that's going on. And in particular, it doesn't know just the static topology, but it also knows all of the dynamic failures that are happening at any given time. And so in the earlier example, if one of the uplinks goes down, the SDN controller can dynamically readjust the weights and make sure that not too much traffic is being sent to the node that has reduced capacity due to failures. And then the last thing we can do is also we can have policy-driven decisions in the controller. So one example of this is that these switches, the way they implement WCMP, at least a lot of them, is by essentially replicating the forwarding entries in the hardware based on the weight. So if you have two uplinks, one with weight 1 and one with weight 2, then you sort of have 3 forwarding entries. So one is for the weight 1 uplink, and then there's 2 replicated ones for the one with weight 2. And so what that means is obviously the sum of all of the weights is going to be limited because hardware resources are limited. So these tables that you replicate into have a limited size. And so the centralized controller can really make sure that the way we use these limited hardware resources are in line with what our goals are. So for instance, we might decide that certain kinds of traffic is more important and we want to have better load balancing for that, and we use WCMP for that. And other traffic that might be less important, we can still do ECMP, even though it's not optimal, but it conserves our hardware resources for more important use cases. All right, so now that I've talked quite a bit about sort of the motivation and like why we want to do WCMP, I want to pivot and actually tell you how is this related to P4, how do we use P4 and P4 runtime to actually make this work. So very naively, if you have a fully programmable switch, what you can obviously do is you can write a P4 program that supports WCMP. In fact, this is relatively straightforward. And then you can take this program, you compile it using the P4C compiler, and you basically get a binary that can run on your fully configurable chip. Now we have a switch that supports WCMP. And in addition to that, you also get P4 runtime, which is this control plane protocol to install the table entries on the individual switches. And so in that situation, you can basically immediately use your SDN controller through P4 runtime and control and set the weights you have computed on each of these switches. So this is very straightforward. Obviously, at Google, we have been using switches for a long time, and we have many different switch generations that we've been using. And a lot of these switches are more fixed function switches that aren't fully programmable. And so what we can do in this case, luckily, these fixed function switches do still support WCMP as one of their fixed function blocks in their pipeline. And we can use P4 as a modeling language to basically describe what the switch is doing or what the switch's pipeline is exposing. And so we sort of arrive at a similar program that also supports WCMP. But here, instead of writing the program from scratch and then telling the hardware what it's supposed to do, we sort of use the hardware as a guide to show what we want the P4 program to look like. And actually, if you think about it, these two models are sort of two ends of a spectrum, where on one end, you have a fully programmable chip, where the P4 program is really determining what the hardware is going to do. And at the other end of the extreme, you have the hardware that's fully fixed, and it actually determines what the P4 program is going to look like. In reality, at Google, we actually do something that's a little bit in the middle. So even though we have a lot of these fixed function switches, many of them still support some amount of programmability. And so we can model that. And in addition to that, we can also sort of model the parts of the ASIC pipeline that we want to use, and maybe now model some of the other things that we are not actually relying on. So for instance, in some of our roles in our data centers, there's not a whole lot of L2 forwarding, and so we don't need to model these tables. And so on. Okay, so now we have a P4 program that describes what our switch does. And I want to say a little bit more about why I really believe in P4 and using P4 in this way. So first, P4 really allows us to model our relatively heterogeneous fleet in a single language. As I've mentioned, there's like many different switch generations, and as time goes on, new generations are going to come online. And so P4 provides us this uniform way of modeling what the switch is supposed to do, and then having the SDN controller have a single interface that can use to talk to all of these different kinds of switches. So the second point is precisely that. Basically, P4 Runtime provides this very clear interface between the controller and the switch. And it makes it very clear what are the kinds of operations that are allowed by the controller and what kind of tables can you program and so on. And then lastly, we also get a very precise specification of what the switch is supposed to do, which really helps with validation. And I want to talk a little bit more about what we do using P4 to validate the various aspects of our system. So let's start with validating our switches using the P4 program that we have. And in particular, let's start with the control plane side of things. So the simplest and maybe most obvious thing that you can do is you can take a switch and you can just replace some production table entries that you know your controller will produce if this were to be used in production, and make sure that the switch is handling these correctly. And this basically covers all of your current needs that you have and explores all of the features that your SDN controller is currently using. But it doesn't really test anything beyond that. And so to address that, we've also built a fuzzer that basically randomly creates table entry insertion and deletion requests through P4 Runtime, and then sees to the switch, and then uses an oracle to decide what the correct behavior is and make sure that the switch is actually behaving correctly. And so this allows you to really cover kinds of use cases that aren't yet used in production. So for instance, if you have a new table that you haven't been programming before, obviously replaying production data will not use that, but the fuzzer will. In addition, the fuzzer is also very good at sort of spotting reliability issues, because it will just randomly hammer the switch and really expose all of its operations. But of course, it's not enough to just check that the control plane is doing the right thing. Just because you can install a table entry on the switch doesn't actually mean that the switch is forwarding correctly yet, according to that table entry that you just installed. And so it's really crucial to do data plane testing. And essentially, for data plane testing, the thing you want to do is you want to come up with interesting data plane packets that trigger all of the behaviors that your switch has, so that you can do very thorough testing. And this is a pretty challenging problem, sort of in the abstract, but because we have a very precise description of what the switch is supposed to do using the P4 program, actually we've made a lot of headway in this problem. And I want to talk a little bit more in detail how we actually do this. So what I'm showing here is essentially sort of a graphical representation of what the P4 program is describing. right? Many of you are going to be familiar with this. So the P4 program first describes how to parse packets in this programmable parser using parser states. And then the program basically goes through a match action pipeline where you have a bunch of different tables. They each have entries that are match action pairs. And then at the end of this pipeline, if the packet hasn't been dropped, essentially the packet gets forwarded to the programmable deparser, and now it gets sent out on the network. And so what we can do with this is many things. One thing is we have these software switches, namely BMV2 in the open source, for instance, and we can take that to basically execute this P4 program on some example inputs, so on some example program, on some example packets. So we can take a packet, we can see how it's parsed, how it flows through this match action pipeline, and what kind of packet comes out at the other end. And so this is really useful because it allows us to basically have a reference that we can compare against when we check that the real switch is doing the right thing. But maybe more excitingly, because P4 is a relatively constrained language. So as Nate has already been talking about, like there is, for instance, no arbitrary amounts of state. There's also no loops, no things like that. What we can do is we can employ some program language, program analysis kinds of techniques, and we can build a solver, and we've done this at Google, that essentially allows you to sort of reverse the program. So what you can do is you can take a packet that comes out of the switch, and you can ask the question, what would this packet have needed to look like such that it got forwarded in this way by the switch? So essentially, you can sort of go through this entire pipeline in reverse. And obviously, at this point, it's not necessarily going to be a one-to-one relationship. So there might be many input packets that all get forwarded in a particular way. So as an example, if the packet that you're interested in is a packet that's encapped in an IP tunnel, then you can ask the question, so what would an input need to look like to the switch such that I get this encapped packet? And if we run our solver, it might tell us, well, there's several options. One option is that your packet came in and it was already an IP encapped packet, and it just got forwarded in this particular way. A second category of packets might look different, and when they come in, are not actually encapped yet. But as part of the match action pipeline, one of the actions is to encap this packet. And so you end up with the same encapped packet on the other side. So this is a really powerful and sort of very general kind of infrastructure that we've built. And one specific use case that we have is for this data plane testing. So as I said, one thing that you want to do is you want to sort of trigger all of the forwarding behavior that your switch has. And one way that we are realizing that is by basically trying to generate packets that hit each of the table entries in all of the tables in this switch. So specifically, I'm highlighting like one particular table entry here. And so we can now ask the solver to basically start the P4 program at this point and reverse execute it to get an input that would have taken us to this particular match action pair, such that the match matches and the action gets applied. And so now we can just loop over all of the table entries in all of the tables and get one or many packets that are actually hitting those match action pairs. And this gives us very good coverage over all of the behavior that we've modeled in our P4 program. So essentially, we've built this infrastructure that takes data plane testing really to the next level, where we can automatically generate packets that hit each of the table entries. We can also do other kinds of things on the data plane side of things. So for WCMP in particular, obviously we rely on the switch hashing the packet and then forwarding according to the weight specified through P4 runtime. And so this is also something that we can test automatically. So basically we have a test that looks at the forwarding entries that you're installing and make sure that the switch is using the right distribution as it's forwarding the packets that are being sent to it. Similarly, there's other features that the control plane cares about on the data plane side of things. There's things like meters, where you want packets to be metered. There's things like counters, where counters need to be incremented, and we can automatically test the packets that we're sending to. are incrementing these counters correctly. And again, for counters, like one of the things you need to do is actually send it packets that can hit all of these different counters, or basically can increment all of these different counters. And so one way we can do that is basically using the first step that I've just described, where we automatically generate these packets to make sure that we have at least one for each of the counters that we want to test. And so in summary, I think the really cool thing about all of this validation technology that we've been able to build because we've been using P4 is that essentially all of these tests are parametric in the P4 program. So what that means is the P4 program is really an input to these tests. And as you change your P4 program, so maybe you want to use a new feature, and so you go from a P4 program in version 1 to a P4 program in version 2. And so all you have to do is basically just rerun all of your tests, and you automatically get coverage for these new features. So for example, let's say you started out in a world where you only do ECMP, and your P4 program only has ECMP forwarding. And now you actually decide WCMP is really necessary to do your optimal L3 forwarding. So in that case, you can basically take the new program where you now added WCMP. You can just run all of these tests automatically, and you can make sure that the switches that you have are actually implementing all of this correctly. And so this is really exciting. At the same time, it also allows you, when a new switch generation comes along, you can automatically use these tests to validate and revalidate that the switch is doing the right thing, and they will be able to interact with the controller software sort of in the right way. So essentially, all of this comes out to that the P4 program is really the source of truth. We use the P4 program as the source of truth of what is supposed to happen in the switch. And this allows the controller to be much more ignorant of the exact details of how the switch is implemented. Like in particular, it doesn't have to necessarily care about what switch generation this is and so on, because the P4 program basically tells it all of the necessary information about what the switch is going to behave like. And so we found this an extremely useful abstraction, even in the cases where not all of our switches are fully programmable. And so with that, I'd like to thank all of you for joining. If you haven't asked any questions yet, there's still time. And I think we're now going to take some time and answer questions. Maybe we can start with some questions from my talk, and then we can also have Nate join again, and maybe there's some questions that we can jointly answer. All right, let's see. So one of the questions that I see here is, does your test framework send packets at line rate? And how do you test meters? Great question. So there's sort of different aspects of our testing methodology. The solver that I've described that can automatically come up with these like very precise packets that are going to hit the specific table entry. The solver is not able to generate enough packets to do line rate testing, not even close. But the good thing is, because these packets are so well targeted, we strongly believe that basically a small number of packets is enough to get coverage of all of your switching behavior. Obviously, at the same time, that means you're not yet testing sort of like that your switch can actually forward traffic at line rate. So this is something that you still would want to do. And for that, we mostly employ sort of more traditional kind of techniques where you have line rate traffic generators that you hook up to your switch and make sure that these get forwarded correctly. The traffic that gets generated there is usually a bit more boring, doesn't sort of cover all of the switching behavior, but sort of these two testing methodologies complement each other quite well. And sort of similar for meters, it depends a little bit what kind of meters you have. So one kind of meter that you care about is that the packet that gets punted to the CPU doesn't exceed a certain meter, and that's something that you can do with the kinds of techniques that I've described. We can generate enough packets to actually do that. So then another question is, can you also test for overlapping rules? And the answer is yes, we definitely can. So I basically sort of said, like, we go through all of the through all of the different table entries, and we sort of reverse execute the program, and we find a packet that actually hits that rule. But one thing that I haven't mentioned, and sort of sweeping under the rug a little bit, is that, of course, not all table entries are actually guaranteed to be able to be exercised by a packet. So depending on how you set up your pipeline and depending on what table entries you install, there might be cases where earlier tables prevent you from ever matching some other thing, or maybe there's overlap in the way you've used priority. That means some of these entries are not going to be able to be hit, and we can definitely detect them. And similar, we can also ask the kind of question where we want to hit a certain table entry, but we make some additional conditions. So a very common example is that if you ask our solver, can you please give me a packet that hits this particular table entry? It will happily do so, but then it will give you a packet that actually gets dropped later on in the pipeline. And that's kind of annoying, because when you then actually send it to the switch, you don't get a whole lot of visibility of what happened to that packet, because, well, the packet just got dropped. And so it's a bit difficult to really gain a lot of confidence from that. So often what we do is we ask the solver to hit a particular table entry. And if possible, we also give it a side condition that this packet entry should not be dropped. So yes, we can definitely consider overlapping rules. So another question I see here is, does the P4 switch need to run ECMP, WCMP, or can the SDN controller compute that and provide weights according to the switch? So the switch is going to require hardware that basically have a WCMP table where you can install the weights so that the forwarding happens correctly. But at least the way we do this at Google is that the centralized controller is the one that does compute the weights. So these weights are never computed by our switches. They're always computed in the SDN controller. Another question here is the implementation of centralized controller local to data centers and zones? And yes, the answer is definitely yes. So the way we structure our networks is sort of highly hierarchical, where we build sort of smaller units and then go bigger. And we ensure that there's a lot of redundancy between these different things. So in particular, our centralized controller is central to what we call a control domain. And these control domains are actually even smaller than a single data center. So within a single data center, there's going to be many control domains. And that ensures that even if one of these control domains fail, we don't have the whole data center go offline. So yeah, this is definitely localized to even smaller units in data centers. One question is, but doesn't the less important traffic's imperfect load balancing still impact the other important traffic? So this is basically a reference to what I was saying earlier, where we have some policy decisions where we decide some amount of traffic is maybe less important, and we won't do a WCMP. So we can do WCMP for the more important traffic. Maybe what I should have said instead of more important is also how much traffic there is of a certain kind. So if you know a certain class of traffic, you're never going to see like huge amounts of spike, because most of the traffic is sort of from other categories. Then it doesn't matter as much whether you're going to do optimal forwarding for that less important or less prevalent traffic. There's one question, it's quite long, so I'm not going to read it in full, but essentially it's sort of asking or pointing out that WCMP, or sometimes it's called UCMP for unequal cost multipath, actually exists in the BGP community. And so why do we go through all of this trouble to do it the way we do, instead of relying on what is already being done in the BGP community? There's a number of answers to this. One is that we've been traditionally doing software-defined networking at Google long before WCMP was introduced. And so this is just like a natural fit of what we can do. And I think the other is that, at least to my knowledge, the BGP implementation still sort of rely on relatively local decisions on computing these weights. versus our centralized controller having the ability to really know the entire topology with all of its failures in mind. So some of the examples that I've given sort of say like, oh, if like one of the links fails for the S2, and then your S1s might want to adjust. But those are obviously some amount of toy examples. And if you have these failures happen very far away, they can still have an impact on what you want to do earlier on with the way you analyze or compute these weights, which is much harder to do with BGP. All right. I don't know, Nate, do you want to take any of these questions?
Sure. Yeah, I'll jump back in. There's a question about adding loops to P4. And this is a topic that's been discussed several times in language design groups. Even bounded form of loops right now require basically cutting and pasting code. So if you're doing the same thing, maybe 4 times or 8 times, you have to actually replicate the code. So there has been discussion of adding, bounded loops to P4 to make that kind of program easier to write. There's even some academic proposals that are very concrete for how to do this. So I think that is something that could be considered. The main worry from adding bounded loops is it does make it easier to write a program that is very costly. With a short amount of code, you could require excessive resources or excessive time to process packets. So that's one answer. Another answer is, of course, if you're considering reaching out to the edge, then you might want to allow even more powerful forms of loops, say of the kind that eBPF supports. eBPF has, at least in the kernel, has a verifier that makes sure that programs terminate, but it doesn't. You can syntactically do loops. So that's a more dramatic change that I think would need some discussion. But certainly, if you enrich the notion of state and you then want to process that state in complex ways, some form of iteration seems like it will be necessary for certain use cases. So the challenge is how we can support that without completely going into a general purpose language with all of the complications that brings. If I could just jump on, there's one other question that was related, which is, I think Stefan's talk showed really some of the benefits you get from having this restricted language. Certain kinds of program analysis or validation tasks that are intractable in the general purpose setting become maybe not trivial, but very feasible. You can do symbolic execution, you can do exhaustive path enumeration, you can generate tests. And again, it's possible to do that for general purpose languages, but you need to do a lot of work to find the right heuristics or the right abstractions to make it scale. Whereas with P4, it's a more direct exercise. So if you add to P4 richer notions of state, richer forms of computation, there will be a trade-off in the sense that verification analysis becomes harder. Again, may not be impossible, but you may need some additional hints or heuristics to make these kinds of techniques work well.
Yeah, I completely agree. So I can take a few more questions here. So one question is, are there any scalability concerns you have observed in fitting weights to switch roles? And yeah, as I said, these weight tables are limited in size, and so we do have to make trade-offs. Our controller can generate very, very precise weights, and we cannot always fully precisely realize them on the switch. But you can always have a slightly less precise realization on the switch that gives you slightly less than perfectly optimal, but still good enough implementation of that. And I see also a number of questions around sort of how quickly can our controller react to, say, failures, and how often do we update these weights? So the controller can react reasonably quickly. I would say maybe in the order of like tens of seconds to changes in the topology, maybe due to failure. And so this weight computation is sort of run on an ongoing basis, and we can react to things relatively quickly. one more question is, are we planning on open sourcing this automatic packet generator and solver? And the answer is yes, we are. I think over the summer, we have some interns that are joining Google that are going to work specifically on this aspect. So that's very exciting.
I'll take one other question from earlier. There were a couple questions about virtual ports and traffic shaping, and also making the traffic manager more flexible to support things like creating queues and packet scheduling policies. So just together, some of this is of course already supported today. So a lot of existing P4 targets already have a kind of layer of indirection between the actual ports and the virtual ports, if you like, that are connected to queues. And they do run, scheduling algorithms to service those queues. There's been quite a bit of work in the research community, and it's still ongoing, for thinking about what the right hardware primitives and low-level abstractions for expressing things like packet scheduling might look like. So one example is there's this PIFO abstraction that Anirudh and his collaborators worked on a few years ago. And there's every year now at academic conferences, there's work on implementing PIFOs or approximating PIFOs. So I think these ideas are bubbling up from the sort of researchy side of things. And I also think that it's pretty clear that there's a pull from above. A lot of the reason that people want to program a network is to have control over these performance aspects. And so, extending programmability from just, what are the packet contents that are flowing through a network to also when do they get there, and how do we control things like scheduling, traffic shaping. This seems like a next frontier.
Another question I see here is the question of whether P4 is running in production at Google or whether this is still more of a research project. And the answer here is a bit nuanced. So right now, we are not using P4 or P4 runtime to control switches in production, but we are definitely planning on doing so in the near future. And I mean, in a sort of organization and network that's as large as Google's, often you have to sort of make trade-offs and do this a little bit incrementally. So the way we're going to do this is that our SDN controller will internally, our SDN controller is a relatively large distributed systems with different parts of the controller interacting in various ways. And so internally, it's still going to use sort of its own abstractions that we've built over time. They're a bit more aligned with what OpenFlow looks like, because that's what we are using at the moment. But then at the edge, the controller will actually translate those internal representations to P4 runtime and send those P4 runtime table entries to the switch. And on the switch, we will have a P4 runtime server that is speaking P4. So that's sort of the near-term goal. I think our eventual goal is that all of the controller is going to be exposed to P4, and that all of the controller knows about all of these things, but that'll be a next step. All right, so I think we're already over time, and I want to be cognizant of people's time. I don't know, are there any other questions that you want to answer, Nate, or should we end it here?
Yeah, I think we should probably wrap up here. I just encourage people to, again, get involved. And if you had a burning question that you didn't get answered, there's the P4 mailing list. There's also a Slack that's linked to from the P4 webpage, where I lurk and lots of other people lurk. So great questions. We didn't get to all of them. There's, I think, about 20 that we didn't get to answer. But please come over to the Slack, and we'd love to continue the conversation there, and enjoy the rest of the summit.
Yeah, thank you, everyone.
Great. Great, thank you, everyone. And with this last question, our webinar has been concluded. We would like to take this opportunity to thank Nate and Stefan for presenting in this informative and interactive webinar. And also, of course, we would like to thank our participants for attending. We will make the recording available very soon. And with this, have a great day. Thank you for joining.